It's a pleasure to introduce today's speaker to those of you who don't know him, which might be like 3 people in the audience, and perhaps those who watch the tape later. But for those who don't know them, and also for those who do, I'm happy to introduce our speaker today, Gish. Herb is from BBN, where he has been for a number of years. He's led a lot of their very exciting speech research. I remember him from my days as a grad student. I came to Hopkins for a summer workshop. These were the days when on switchboard the error rates were 85%. And on Spanish telephone speech, switchboard Spanish, I think the error rates were 105, Herb? Yeah, at times are 105% error rate. But of course, he's done a lot of good work to get that down to the 20s and 30s. Just on an academic note, he started off as an electrical engineer, but then he got himself a PhD in applied math. And so, Carrie, we do have applied mathematicians in our fold who do real speech. Without further ado, Herb Gish.
Unsupervised training of an HMM-based speech recognizer for topic identification. This talk is really dealing with the extreme case of speech recognition when there really is no transcriptions. We know how easy speech recognition is when you have transcriptions, so just kidding, guys. But I think it's useful to understand if you don't have any transcriptions, are you out of business? What can you do? How can a little transcription help you? And that's what I will explore today. And again, this is sort of a work in progress. I will not have answers to all these things, and a lot of things still need investigating. So we're going to start off with a segmental Gaussian mixture model. I'll try and tell you what this is, some examples, and it's going to be our baseline approach. It's not an HMM, but it's certainly simpler than an HMM, and it's going to be connected to an HMM later on. And then I'll talk about training our HMM system, Biblos, why we're doing that, and it's going to be provided a transcription from the SGMM, segmental Gaussian mixture model. And by the way, any questions or heckling can happen at any time. Yes?
When this happens, touch the screen.
Oh, this buzzing sound.
The
yes.
buzzing.
Just touch
The screen?
No, it's not yours.
What screen? Fourth screen. That one.
When it wakes up.
Oh, okay. Gotcha. And we're going to look at some problems related to topic ID. One is finding snippets, and I'll tell you what that means. It not only, sometimes you want to classify a whole conversation as to being on a topic, and sometimes you just want to find those parts of a conversation that are on a topic. So we'll look at both things. Those are snippets. I'll do some performance comparisons. And then if we have time, I'll talk about how this unsupervised approach can be used in keyword spotting. Okay. These are some of my colleagues, me and some of my colleagues who've worked on this technology. So why do I want to look at this? I mean, again, I explained that it's the extreme case. If you can do something without any transcriptions, there's no reason to hesitate. You can just go ahead and do it. You don't have to wait for transcriptions. I mean, a lot of times people say, well, we want information out of a collection of audio, but we don't have transcribed data, we can't do anything. And that's not entirely true. But so we're going to explore what we can do under those conditions of no transcriptions. And then we'll also look at what happens with a little transcription. And so those are the first few points. And I certainly explore related applications such as keyword discovery. And more generally, what do you have to know about, how can we extract information with minimal resources in general? What will we do with an hour of training? What's going on? The approach. It's sort of like when you're starting with nothing, all you have is acoustics. You got to learn about your corpus, and it's sort of like a sequential process where each stage gives you a little more information about the corpus you're dealing with. And then you can sort of build up knowledge as you go along. And this, one of the things we'll look at is how we can learn enough to provide a transcription for training an HMM. And the approach we use uses discovered sound units. I call them discovered. That just means that they're not predefined. They come out of the data themselves. I'll talk about that. And again, that's SGMMs are going to play a role. OK. So what do we have? What are the constraints? No language sources, no or very limited transcribed data. I assume we're going to have topic labels. By a topic label, I mean there's some acoustic data that you said, this stuff is on the topic, and this stuff is not on the topic. That's the totality of required annotation. And it doesn't require, you don't have to be a linguist, just have to know what you like. So the approach, again, automatically discovered units. How do we get them? We'll be doing speech segmentation, clustering of segments, using the segmental Gaussian mixture model, which will come from those clusters, as both for defining the units and as initial tokenizer. Then we'll tokenize n-grams to build a classifier, generate the features, tokenize it of the n-grams. The n-gram will serve as features for the classifier. And we'll use Biblos technology for the improved acoustic modeling, improvements over the segmental Gaussian mixture model. And as a classifier, we'll be using an SVM or decision tree classifier.
When you say topic labels,
yes.
Is this only one label per conversation?
One label per conversation.
And what percentage of the conversation has to be?
These are the switchboard labels of conversations. I'm using switchboard corpus. We know that on switchboard, two people will talk, and they'll go in and out of a topic. So, and it's variable, and it's basically using switchboard. This is what it looks like. A topic classifier, the models define the tokenizer. Audio comes in. We have features from the tokenizer, and we go into the classifier. And that's sort of the system that we're building. So let me talk about segmental Gaussian mixture models for a second, because they're going to play a role here. Basically, for each cepstral feature vector at frame n, we assume a model for a sequence of capital N frames that the cepstra can be characterized as a mean plus a residual. And this is a vector mean. And the model for the mean is going to be a polynomial. And so we basically have the elements of a segmental Gaussian mixture model starting to emerge. This is just what we do for an initial segment. We model it with a trajectory in feature space. And when we finish the modeling of any particular segment, we end up with a set of parameters. One, a matrix of defining the trajectory and all the features, a covariance function defining the residual and the number of frames that were in a particular segment. And that's, once you have that set of statistics, assuming it's a Gaussian residual, you basically have the sufficient statistics to evaluating the likelihood for any segment. So at this point, you can throw away your data once you get that. But the mixture model is basically an ordinary mixture model, but X is now a sequence of frames. X is a sequence of vectors. Mu j is that trajectory of the feature vectors in the segment. And sigma j is the covariance of the residuals. So basically, what you have there is what I'm calling a segmental Gaussian mixture model. It's like an ordinary Gaussian mixture model. But an ordinary Gaussian mixture model, the mean is a vector. But here, the mean is a trajectory in feature space. So each Gaussian sort of represents a sound. And so it's a little more general. Basically, an ordinary Gaussian mixture model is when your trajectory is x bar, a constant vector. Here, we're allowing dynamics in the mean of the Gaussian. I'm not going to really address the issues of how we train this system and how we actually learn the parameters and how we mix segments of different duration. Basically, all segments are normalized to unit length. And it's basically, we can do EM training a little more complicated way than ordinary Gaussian mixture models, but you can do EM training to learn this Gaussian mixture model from a collection of segments that you will normalize to unit length. Yes?
On a previous slide, you used a second order polynomial for the mean.
Yes.
That's based on your experience and model selection, and you got enough to do that and not more?
We haven't gone more than that. Not that more wouldn't help, but just one of the avenues. We tried linear and quadratic, and we basically just stayed with the quadratic.
It's a short segment.
Right, but you didn't do any sort of careful and model selection analysis. You just that works.
That worked the best on some problems.
Thank you.
And again, there's issues with small segments that I won't get into. And some of the problems with this approach are what happens because you have all those small segments. If you only got 3 frames, you've got a degenerate model. But I won't get into that.
Any feeling for how the segments line up with what we think of as phones?
Yeah, that's one of the things we have done is map, do a phone to analyze. We've done alignments to see what units map into what phones after we've got them.
So a segment is a whole phone, or?
Sometimes it can be more than one phone. Sometimes it'll be a syllable, and sometimes it's a phone, and sometimes it's something you never heard of. Yes.
You also model the covariance as a trajectory or as a constant.
That's very interesting, because I was going to get into that too. But indeed, we have found, now here we use constant covariance, but over for a whole segment. But we have experimented with having time variance covariance matrices. This is sort of like changing states. As covariance changes dynamically over the segment, you can actually do that modeling. We've done experiments on that, and it actually improves performance. It's a lot more complicated, but indeed you can do that. But that's a generalization of the model for having time-varying covariances.
So basically, you're normalizing these means to unit length. All these
the segments. The segments.
To get the same quadratic form for each other, so that they don't get loop compressed or overlap.
That's right, and it facilitates the combining and utility of the model by having a normalization to unit length. But so that's. What's that? Oh, sorry.
Thank you.
You need a page turner here. Sorry. Okay. So how do we convert? We have a segmental Gaussian mixture model. How does that become a recognizer? Well, it becomes a recognizer or a tokenizer. I'll use those terms interchangeably by using. You get a segment. You normalize it to unit length. You find out which term of the Gaussian mixture model is maximum, and you put out the index. Term J is maximum. That's what that segment produces that token. That's our baseline recognizer. Now, you have to understand this is a pretty simple recognizer. It's one Gaussian that has a time-varying mean for every sound. There's not a lot of characterization there. It's pretty crude. But, by the way, you could also produce soft decisions by having the probability of being in a particular term. Okay. So let me just review the steps in training the SGMM. I'll call it recognizer now. Segmentation of the domain data segment. And this is what we tell the segmenter. We base it on, we say a segment boundary is defined by spectral discontinuities. It has no parameters that we have to put in. Everything it knows is learned from the corpus. And it automatically trains models to detect discontinuities in the domain of interest. I'll give a reference to that. This is work of Jordy Cohen, actually, a long time ago, who came up with a technology for doing an adaptive segmentation where you learn what a discontinuity is from your corpus. So it's corpus learned. So there's a lot of smarts in the segmenter. Doesn't mean it works that well, but modeling of each segment. So again, each segment is fitted with a polynomial segment model, time normalized. And now once you have a model for a segment, you can ask, what's the distance between this segment and that segment by comparing the models? And there are a variety of ways of doing that. I didn't want to get into them all now. We've used generalized likelihood ratios as distance measures, but now we're using basically, you have a trajectory over unit length for segment 1. You have a trajectory of, defined by the mean. You have a trajectory for segment 2 over unit length. And look at the mean squared distance, for example, between the trajectories. That can tell you the distance between the segments. Again, model-based. And the creation of the segmental mixture model, each term is initialized by a cluster from the segmentation. It's EM trained, and again, this is how you end up with the Gaussian mixture model.
So once you segment it, that's the segment.
That's the segment. You don't revisit the segmentation. That's done. Then you go on to segments, to model segments, to cluster segments based on the distance between segments, and you pick the number for the number of units.
So 2 questions. One, following up on Tom, would it help, do you think, to resegment, in other words, to treat the segment boundaries as something as hidden variables to be learned by EM?
I think it would help. Yeah, as a matter of fact, we let when we train I'll get into it. When we train the HMM, this is only an intermediate stage. The SGMM is going to truly create a transcription and give the labels to a hidden Markov model, which will do its own segmentation. But you are stuck with the labels that came from this initial segmentation, and there is a real issue. One of the issues is what's the best segmentation? We haven't explored that a whole lot. We've looked at different segmentations, and they do make a difference, but yeah.
And the other question, if there's time, I was surprised that you're completely normalizing for time, because I'd expect the magnitude of the movement to have something to do with the duration of the trajectory. Is that true in the observed data? Or?
I would think one can extract information about the unit based on duration, and one is losing something, but one is also gaining something as one of those trade-offs.
Yeah, you could just imagine putting that in as another parameter.
Exactly. We've considered that. Right. The original duration can act as a feature. Yeah.
If I have a technical question,
yeah.
Maybe you have to answer it offline.
Oh, yeah.
In the segmental GMM decoding, I'm trying to figure out whether the dynamic programming still works out, because if you hypothesize something for k segments and then you want to continue it for k+1, the unit length thing means that you recalculate various things in the past, because all your means move. Does that pose a problem, or am I not?
Well, I don't think. You do a segmentation. There is a segmentation that is fixed when you do the decoding.
Oh, even the decoding is fixed.
Exactly.
Oh.
It is not like an HMM where you're learning, and there are ways around it, but it's complicated. But it is not doing the dynamic programming aspect, because that's a real serious issue, and we've gotten around it. But it violates that basic assumption: don't make any decision until you have to. But one can argue from the point of view of robustness, sometimes leave it. And by the way, we use a different feature set for segmenting than we do for the HMM. And just because you can, in other words, there's a bit of a trade-off. We use spectral bands actually, for segmentation, whereas in the HMM, of course, we use Kepstra, and we find the segmental bands work. The spectral bands work better than Kepstra for that.
So, how many clusters?
Your choice. We pick.
Do you set it?
You said it. That's not learned. We said it.
And you set it.
From 50 to 200. You can't go out of. No, you can pick whatever you want, but 50 if you think they're like phonetic units, and in the problems I'll be doing, I think we use 64. Okay. Speech segmentation. There are a lot of ways of doing it. We've stuck with one, but we're investigating other ways now. So we're grouping together acoustically similar adjacent frames, and the segment boundary depends on spectral discontinuity. Jordi Cohen wrote an interesting paper on speech segmentation a while back, and And this is one of the keys, is the learning of what's the statistical model between adjacent frames that are in the same segment and things that are in different segments, and that is learned, which sort of makes it invariant to having to set parameters. What's a spectral discontinuity? You don't have to set it once and for all. It's learned by the segmentation algorithm. There are alternative approaches we've been looking at, but this has been our main approach, but it can be an issue. So, I mean, what are we looking for? I mean, this is the basic spectrogram with spectral bands, and there's the acoustic waveform, and this might be a spectral discontinuity, another, and you may end up chopping it up in different places, or maybe not. But you can see, you can imagine places you would put spectral discontinuities, based on looking at spectral bands. And that's, I think, how we look at these waveforms. Is when we look at these things, that's how a linguist might identify things based upon bands and discontinuities. So this is our baseline system. This is what we've got. I've went through those steps already, but basically, once you've got a recognizer, the segmental Gaussian mixture model recognizer, you then can segment, you can recognize the data that's been labeled, so map that data into phonetic units, discovered units. Once you have the discovered units for the on-topic and off-topic, positive and negative examples, you can build your support vector machine. So this is how we're learning all along. Still, all we have is labeled data, it's the topic. And now we go ahead and set the support vector machine to classify.
The segment recognizer, that's Biblos?
No, not yet. This is just this SGMM. Right now, the segment recognizes the segmental Gaussian mixture model, putting out tokens based on.
But you don't pre-segment the
new
audio, or
yes, we do. Right? At this stage, in this process, everything is segmented, both in training and in testing and evaluation. And in test audio, we do segment, and then we recognize, and then we actually generate the features, which are going to be n-grams of the sequence features, and then go into the classifier, and we do a classification. The question is, have we done anything useful? So I think I've talked about all these properties. I think we have demonstrated useful performance, but why don't we take a look at some of these things? There are alternatives, by the way, to the classifier, and I'm going to give. And we'll look at these. One is phonetic recognition, and we'll use Biblos for that. We're going to build Then there is the state-of-the-art recognizers built by BUT. If you have any questions, I think you should ask Hynek about them. And these are models we'll also evaluate. I think we're just going to look at the Hungarian recognizer. And the question is, here it's been trained on some domain. We're bringing it to a new domain. It was a telephone channel. Do we bring it over to the new telephone channel? Will it still work? And you'll find it works pretty well. There are a variety of ways of improving, as an alternative model. I think we've talked about segmental Gaussian mixture models, one Gaussian. You can use more than one Gaussian. And you also actually can use HMMs, even at this stage of the processing, to replace the segmental Gaussian mixture model. But I want to give an example. So one of the first things we did when we trained up a model, we were working on switchboard, and this was, I won't go through the corpus or whatever, but we found we were using tree classifiers. We generated all these synthetic units, and we said, okay, let's see what we're finding. Pick go to the tree classifier, find a unit that looks like it's doing some heavy lifting. It was a bigram feature going to the SVM, into the tree classifier that was important. So we found an utterance, and the topic was automobiles versus not automobiles from the switchboard corpus. And we said, okay, let's see what the utterance is that maps into this, that's using this feature to say it's on topic. And so this was actually the first thing. Oh, we looked at. And this is when we went to the utterance that contained this important feature, we heard. Now that's the cut from that we found when on the car topic, with someone saying Ford Thunderbird. so that was a lot of fun, and we knew we weren't doing just terrible things. So, and I'll give another example, and I won't.
So sorry, that tree classifier was retrofitted to the SVM?
Oh, no, we weren't using the SVM at that point. We were just building a tree classifier based on the, we use both tree classifiers and SVMs. Now we only use the SVMs unless we want to figure out what was actually going on a little bit. Then we use the tree classifier. At that time, we were only using the tree classifier, and this turned out to be one of the important features in the tree classifier.
So somewhere I lost track of how you train either of those classifiers unsupervised.
Oh, well, you basically you have to go back, because you have label data. You have on topic, cars, off topic, not cars.
Okay, thank you.
And then you recognize both of them and tokenize them with your
That part's not unsupervised. Okay.
No, in the sense you have the labels.
Got it.
Yes.
So the acoustic labeling is unsupervised.
The acoustics are all unsupervised, but one of the assumptions is you have labels for topics, things you like or don't like. Yep. Yes. Thank you. Okay. And so this same again, here's the example. We built a tree classifier for this problem. This was let me go back. Cairo radio. It was broadcast. Topic was all conversations broadcast about Hosni Mubarak. And again, and this time we were using pentagram features to find, build a tree. And the tree that came out was this. And this is the feature. This is the best feature. It says if it's there, hey, it's on Mubarak. If this one's there, it's on Mubarak. And then, so of course, you can't resist it. You go back and say, what is that feature that is so certain? And then you go to the utterances and you play it, and sure enough, and then I'll play, it's different speakers. And you got one from each. There were both two pronunciations of Mubarak. And if you go to the actual, time interval that's specified by the pentagram, where the pentagram begins and ends, you do end up. That's just one Mubarak. But you do end up with something that makes sense. And if you look at the two Mubaraks in terms of the segments, they're different but similar. And there was enough capture of variability in the models to go ahead and say these two things are slight variations of each other. Yes?
Quick question.
Yes.
The on-topic, off-topic
Yes.
label, that's assigned to several minutes of audio?
Yes.
Yes, so you're not saying here's something.
Oh, no. It goes to the whole conversation.
Right, so
The whole broadcast. The whole broadcast was on it or not. It's not on any subparts. Yeah.
Is there any speaker normalization that you do when you're doing this SGMM?
Not at this stage. We hadn't. But it helps, which we do later. And okay, now acoustic unit recognition. So two approaches. One is the standard approach. One is no manual transcriptions. Let's use the SGMM is actually producing a transcription. Hey, we have a transcription. We can train Biblos. What?
It's in a script you don't understand.
It's in a script. Of course you don't understand. You don't know what the units are, but it is a transcript. And so Biblos can be trained from labels. It doesn't need segment boundaries. And so you give it the label sequence that came out of the SGMM, because the SGMM is not a very good acoustic model. It doesn't have enough parameters. We haven't made it as good as can be. And we all know how much time and effort we have put into making an HMM really first-rate acoustic model. And Method 2, and I'll talk about that too, we give it 1 hour of switchboard transcriptions. Of course, not from any of the topics we're dealing with. So those are 2 ways we're going to train it. And this is what it looks like. I mean, it's pretty simple. I mean, you go through all the steps. This encompasses the segmentation and the clustering and the decoding of the data, and SGMM labels the training data, and you put the acoustics and the SGMM labeling into Biblos. Okay. And here's why you use Biblos. This is all the features this model has. I mean, and these have been tuned and worked on with tens of thousands of man-hours of labor figuring out. You know, vocal tract length normalization, you get that for free. Speaker adaptive training is in there. Use of discriminative features. Discriminative training criteria, we haven't used that yet. Multi-stage GMMs and how to tie things together in context-dependent phonetic units, and lattice decoding if you want to use that. And actually it'll build a language model for you as you go along too. So that's why we want to go to Biblos. It knows how to do these things at the push of a script. Or say a button, but okay. So we're gonna take a look at a couple of topic ID experiments. First, actually that will be second. But the 2 experiments will be topic classification, and we're going to measure equal error rate with a variety of acoustic models. And I'm going to also look at, and first I'll look at classification of snippets. That's where we label sub-conversations as to whether, sub-parts of, snippets, which are 25 segments, as to whether they're on topic or off topic. And they're on topic. We don't train with this. We just use this for truth. If it has some set of keywords that we have found and said these represent the topic, just to see how well the approach is working. So we take 25 segments in a conversation, put it through the support vector machine, and label it as to whether it's on topic or off topic. So we want to, this is a small amount of the conversation. Even though it might be on topic, the whole thing, we want to look at the little parts. And so those are the snippets, 25 frames. And we look at the precision of the number of correct in the top 100 scoring snippets in a conversation. And that's how we compare, and we compare it to random selection of snippets. That's sort of what I call a force multiplier. If you're just sitting there picking snippets at random, you'll get a certain performance level. If you're picking them according to this using the SVM, you'll get another performance level. The precisions, the 2 precisions, the ratio is what we call the force multiplier, or how many people you will have replaced picking at random, or now your one analyst can do the work of X and force multiplier worth of analysts. So this is what we're doing, keyword detection.
I went over the task definition again, if you just back up on
Yeah.
So the idea is that I have a 5-minute conversation.
Yes.
I'm going to chop it up into small snippets.
25 segments.
And then the task is on each snippet to decide whether or not it's
on topic or off topic.
And there's no judgment being made about the whole conversation. It's guaranteed to be on topic.
Yeah,
so
right.
At least one snippet.
Yeah, right.
And the question, and the efficiency will tell you how many snippets you need to look at before you find the one or the few. Or
right. Right. If you pick snippets at random, that's without any. That's working without any tool at all. And then you can use this tool. It'll give you a precision in terms of if you pick 100 snippets, what fraction of snippets will be on topic versus the random selection. Is that ratio, those precisions.
So the goal is not to discover this conversation in a large corpus.
No.
Given a conversation, show me the relevant segment.
So yes, so it's looking at a smaller scale. Yeah. Can you localize?
So it's like a web search thing. I know that there are relevant snippets in this conversation.
Yes, we're on it. We're on it. Yes. And this is just describing the 2 problems. Keyword detection, which I'm calling the snippet problem, and topic ID, which one uses topic conversations. Actually, we use topic sides. But anyway. And then you can also go to snippets to keywords. So this is how this thing grows. You get new applications. You've got a snippet. You have a whole bunch of snippets. They're on topic. Well, let's analyze them and find recurring n-grams. And before you know it, you've got a keyword. And you didn't even know what a word was. So this thing grows. You learn more and more about the corpus.
Hey.
Oh, ooh. What was that? But this is what the process is in finding. You put the snippets in, goes through the classifier, and let's see if I can just play. This is a whole, utterance.
Recyclable bags to put the graph, to put things.
These are the topic is recycling, and it's looking for snippets and recycling.
Wish we could recycle as magazines, but they claim that the
So
either computer paper or different types of paper. I've had some ideas on.
So all these are things that the classifier.
Computer paper or different types of paper. I've had some ideas on.
And so these, it's finding snippets that have these keywords in them, and then you find you basically go back and find commonly recurring keyword, those things that occur a lot in the snippets. Which n-grams populate the snippets?
Paper. Paper. Striking.
I don't know what that one was. And you find a lot of so those patterns of n-grams are tying into the keywords by just matching n-grams, and this is just more of the same. This is very sensitive. And these are different multigrams that have come out of this whole process. And yeah. Oh, sorry. I'm immune to it. I have a notch filter. And these are just patterns of different variations of things that recurred again, many times.
Recycle.
Different people saying it.
Recycle.
And so this comes out, you found this pattern, and it's recycle. So again, you didn't know that these were words. Now you can go ahead, by the way, and at this stage, you can go out to new data once it has been tokenized and do keyword searching. You now have the keyword patterns to search for that you found from your initial findings in an automatic way.
And I guess you probably need the maximal match, right? Because of course, you could always find fragments of the same word.
Yeah, but that may not be bad. You don't want to stay with anything too short though, Yeah.
So the recycle is kind of obvious.
Yes.
Recycle, but paper and paper and paper could be about printer. Could be a conversation and also about printer.
Yes, it could be. And maybe.
But if we tagged it as recycle, I guess.
Well, we could talk about building classifier. I would look for something that might have recycle and paper in it. But that goes into the keyword searching algorithm, But here you do find the keywords, some of them more useful than others. But indeed, that keyword could be more indicative of one topic than another. But maybe you look for, if you want better precision, you look at the joint occurrence of a collection. But okay.
The word paper may not have appeared in other topics in the switchboard.
So now I'm going to go to acoustic modeling experiments, where we take a look at the variety of classifiers we have and their performance on topic ID experiments. This is just tables of interesting numbers, or not in depending. So let me just, this is just there were 10 topics, 361 conversation sides, 64 units were the number of units in the SGMM. The evaluation set, there were 19 examples, 680 non-topic. Keyword detection. That was for the snippet. That's out of place. I should have shown that one before. That applies to the snippets, but we're really going on to assuming I've trained the Biblos recognizer. So here's what we get. That SGMM, and everything I've been playing so far came out of the SGMM, and its force multiplier on those snippet problem was 2.94. the higher the number, the better. So we see that Biblos training, just using the output of the SGMM, takes that 2.94 and makes it into 10.7. Then we see that this is, by the way, some sort of vocal tract length normalization. We haven't quite finished doing it. But it increases the false multiplier on the Biblos by 10%. Now the BUT Hungarian recognizer is doing very well. And we have to, what? 10 hours of Hungarian telephone data. So it actually has 10 hours of training. Now the issue is, well, how will it change from channel to channel? Will there be channel mismatch issues? Now this is Biblos trained on 1 hour from the domain. So that's making Biblos into a phone recognizer. Well, no, not, yes, a phone recognizer using standard phone sets, using 1 hour of training. And this is the topic ID problem of the equal error rates for your basic topic ID. Here, the lower the better. And it pretty much corresponds to some degree of higher here. They're doing equally well on both tasks. In the sense that Biblos is doing the best here and the best here, and this is doing the worst here and the worst there. And so these are two tasks. One is topic identification based on whole sides of conversations, and the other is the force multiplier on the snippet problem. And so we see that all the features of Biblos really pay off in a very large way of being able to go from the 2.94 to the 10.7. And if you give it 1 hour of training from the domain, 1 hour of transcribed data, then you go up to 14.6, and it gives the best also topic ID. But the question is, maybe if you don't have any transcriptions, you still get a false multiplier of 10.7 or equal error rate of 24.2. That's without any transcriptions at all. Now, if someone goes out and gets an hour of transcription, you're down here. So an hour of transcription doesn't seem like a lot, but it really impacts on your performance. But you don't have to do it. You could still do reasonably well, well, it depends on your criteria.
So an hour of transcript assumes this speech has a writing system.
Yes. Yes, well, that's one of the problems with transcriptions. If you take some dialects of certain language, you first may have to invent. Yes.
Why do you need words?
No, you don't need. Well, any orthography that.
An IPA transcription would do, wouldn't
Yeah.
Now you're saying let's do a phonetic transcription.
Well, that could be painful, but yes, you could.
But I mean, you don't need to have. The writing system's got nothing to do with the performance of the.
Yeah, but I'm thinking, I'm thinking if I pick up the language, how much does it cost to transcribe an hour? It's not a lot if you have a writing system. But I don't know. I don't have much experience. My experience has been $1 a phone.
You just get an unemployed phonetician.
Yes, you could do it into, yes, a standard set of phonetic units, just like the Hungarian recognizer is doing it automatically. We don't, it's coming out with Hungarian units. Maybe better than an unemployed, linguist working on.
A very small, well-characterized vowel set.
Yeah. Yes, it is.
Are these good EERs? You said insultingly.
I can get them down to 0 if I use Biblos fully trained. So what's good? If I give me not even a state of the art, something with a 40% error rate, or even larger, 50%, I might get down to much lower.
This is binary decision topic ID, right?
This is binary decision, yes.
Do you roughly remember what error rate you got over 1 hour?
Oh, there's no words here. There's.
No, the Biblos was 1 hour transcript.
That's phonetic.
Oh,
That's, It's putting out phonetic units. You have a phonetic dictionary and the word transcription, but we're building making Biblos into a phone recognizer. Yeah. Okay. Another thing we tried was feature weighting or feature selection, and there are a variety of ways to do it. We're running a little bit out of time, and I'll just say the one I'm going to show is a method developed at the Lincoln Laboratory where they go ahead and they build SVMs. They work on a different problem, but they look at SVMs, look at the weights of the SVM weighting particular features, take a look at the big features, which can be n-gram features, and then for those the ones with the biggest weights in the SVM, they go ahead, and they assume they're good features because they got big weights. They go ahead and add a word from the left, and a word from the right, and make a bigger n-gram out of it. So it's not feature selection as much as, well, it is, but feature addition. They're not taking anything away, they're adding in. And that's the only one I used here. And this just tells you how, that's the block diagram of how to do it. Read their paper. What? Oh, thank you. Yeah. You basically, do your training, and you basically end up finding the big weights and extending the n-grams by going back to where they occurred in the training and adding on what's on the left and what's on the right. And it works pretty well. And just to show now, this is that same table as before with one more column. What happens when we do feature, increase the feature set, and some things gain more than others, but it's pretty good increases, respectable increases all over the place. Here, again, the smaller the number, the better for this fairly big changes, actually, in terms of, these two columns you have to compare. It's the topic ID problem, equal error rates that are in those last two columns. So feature selection works. Now, I had there's a whole other application I don't think I have time to get into. I don't know.
About 12 minutes.
Okay. I'll give it a shot. So I just wanted to extend the application domain. So we're going to now do word spotting. Of course, without words. Or not a whole lot of words. And so you can look at word spotting as a topic ID problem. You have every utterance that has a word is a particular word as being on the topic. And every utterance that doesn't have that word as being off topic. So now, if you find the utterance and do a classification, you're classifying it as to whether it's an utterance with a particular word. So that's word spotting. You don't localize it any more than the utterance, but it's word spotting via topic ID. Method 2. This requires transcriptions. But what we do here, and this will enable me I'll just say it in words, and I can skip a whole lot of view graphs. But the idea is, if you have a transcription, again, into let's say an orthographic transcription into the letters of the language, and you also have a transcription in terms of these units. Well, now you have two transcriptions of the same audio. You've got the letters, you've got the sound units, so you can now build a mapping between the letters of the language and the sound units. And it's a multigram mapping. It's not a one-to-one mapping. It's multigram, meaning this letter may go into these pair of units or a triplet of units and vice versa. And so it's a complicated problem that people have worked on. We've applied it to the problem of now creating a mapping from the letters of the language to these units. We don't know quite what they are, but we don't have to know. But when you spell out a word, you then can expand it in terms of the units that we have found. And then you can do keyword searching on those units, because you're basically creating a dictionary on the fly. You type in the word, here's your transcription. And so those are the two ways of doing it. And again, this is what I said already, trying to cut it a little short. This is word spotting, as topic ID. And so we found utterances that had the word familiar. This is really to be expository. And that became the topic. Any word that had the word familiar in it became the topic, any utterance. And if it didn't, it was off topic. And there was a training set of utterances of 23 contained the word familiar. And so by training set, I mean this is a topic training. These utterances that contain the word familiar are now the topic. You transcribe them into these units. And you build units for on topic and off topic, just like we did before. And again, this was able to find, using bigram features, ended up with a classifier that gave about a 20% equal error rate on finding utterances that had the word familiar in it. And that's the ROC curve for the word familiar, And I do talk about what does it mean, what does an ROC curve mean. It's hard to get a lot of information out of that ROC curve. But I took the numbers off the ROC curve and I converted it into one of these factors of a force multiplier. And the force multiplier turned out to be 3. You're able to take it turns out, and I won't go through the algebra, it turns out if you have a needle in a haystack problem, you can look at an ROC curve sometimes. And if you look at the ratio of PD to PF at any point, that will almost give you this force multiplier factor. It's pretty, just basic algebra. I won't go into it. So here, this word spotting as topic ID gave us a force multiplier of 3. We did 3 times better in terms of extracting stuff than you would have at random. Okay, now on to sound patterns. I'll skip the motivation. But basically, you train, you have untranscribed speech, you build a SGMM. No. Yes, that's too general. That's just SGMM training. Well, one second, hold on, is that? Okay. So basically, when you end up with basically the text transcriptions and segmental GMM outputs for the same acoustic utterance, and you build a joint multigram trainer. We based ours on the work cited here, Deligne and Yvonne and Bimbo. And we modified it somewhat, but basically their sort of approach of doing all possible alignments. And so you end up with a mapping that will enable you to go from the letters of the language into the sounds of the language. And searching, you do a dynamic programming search of the strings that you have discovered. You type in the word familiar, the multigram model gives you the sequence in terms of the sounds of the language, and you do a search. And that's just a graphic of a dynamic programming search. Oh yeah, the amount of transcriptions we used was 15 minutes. So in other words, you have 15 minutes of acoustic labeling. In other words, there were 15 minutes of word level transcription used to create the multigram mapping.
If you go back one slide,
yeah.
Let me make sure nobody got more. So one thing I think I noticed, and tell me if I got it right, is that in the previous examples where you're doing topic spotting or you're doing other things, somebody had to listen to speech and label some part of it as on topic and off topic for every target topic, test topic of interest.
Here's what we did. We came up with a set of keywords, manually picked. And we said, that every utterance that has that keyword in there will be declared on topic. This was all done manually for the purposes of evaluation.
But it looks like over here, if you still have to do that for purpose of evaluation here, but when it comes to training, for example, you don't need any speech in the training to be labeled whether it contains the word familiar or not.
No. As a matter of fact, after the training, you can search for words that never occurred in the training. Right. That's the beauty of it.
It's like cross-lingual IR. Yeah. The text is in one language, namely the language of your SGF.
Yes. So, yeah, right. And as a matter of fact, this is the examples of the words. They were, and De Niro had 0 occurrences in the 15 minutes of training. And Trabajo had 1 occurrence in the training.
And so in that sense, the 15 minutes of transcribed data is the data you need for training your translation.
Exactly. You're learning the translation between letters and sounds. That's, yes?
There's no reason you couldn't have done this with spoken query word spotting, right? Doesn't run the recognizer on a query, scouting patterns that way and run against this?
You could have.
Is there any reason to think that wouldn't work well?
Well, you got to have a recognizer that works reasonably well. But this is a minimalist approach. And so some of the words had occurred in the training and some not. But if you learn the mapping, you don't care. And then here's a whole bunch of ROC curves for each of those words. And the bottom line is words that had 0 training are doing just as well as words that had a little training in there in the 15 minutes of transcription. And these two are giving about a force multiplier of around 300%. And so you're doing word spotting now with 15 minutes of training and having learned how to transcribe into these units into the letters of the language. So, well, there's a lot of things to do.
Yeah. If I understand correctly, your translation model is a mapping from phonemes to the sound models that you are discovering?
Not from phonemes, from the letters of the language.
So what if I don't see a particular letter in the training data?
You've hurt yourself. If you don't see it in your query either, you haven't hurt yourself. But yeah, you've got, it was done in Spanish, by the way. That was a Spanish, and that's probably more amenable to letters and to sounds than a lot of other languages, as I'm sure a lot of people here will attest to. So there are a lot of things more to do. This is a work in progress. There are a lot of issues. A couple of highlights. One, I'd like to use HMMs instead of the SGMMs in modeling the clusters. And that would lead down to here. It's sort of like a kind of fun idea. If I fully integrate with Biblos, you sort of have Biblos then. It's an HMM into an HMM, and you have 2 HMMs make an HMM, and you sort of have Biblos generating its own transcriptions to train from. So that's sort of a nice notion. And then there's a sort of theoretical issue of what's the best tokenization for those with a theoretical bent. I don't have any truth when I pick units. How should I build these models? Should I use something like the MDL criteria? Is there some entropy criteria? Is there some rate distortion function that one can apply to a problem like this and sort of train to a criteria instead of training to the application result? I don't know the answer to that. I mean, you got to be a little careful, but there might be things to do. And segmentation, we can do better. We've done various segmentation. We actually tried uniform segmentation. You got to keep yourself honest to see how, to see you're not really, how well you're doing. And I have to tell you, to a degree, uniform segmentation worked too. Which all that tells you is you could do a lot better in segmentation. And why is uniform segmentation doing so well? It doesn't have any of the short segments, that's for one, that create difficulties, but at the same time, it's pretty stupid, and things like that. But
if Doddington was here, he would say that's because syllables always go at 250 milliseconds a syllable, and that's the basic.
And I would agree with it. Yeah. Well, that's it. And any questions? You've been asking questions, but okay. Thank you. Okay.
I'll ask another. So the segmental GMM decoding, how
Yes.
does it compare in terms of decoding time with, let's say, something like the BTU, the BUT recognizer, or the Biblos trained on an hour speech doing phone labeling? So both of them, I suppose, are running as phone recognizers. Is the segmental thing faster? I mean, it has two stages.
Well, it's very fast. It's very fast. It doesn't have anywhere near the complexity of an the H.
An order of magnitude?
I don't think we've measured it, but it is faster. But it's one of the things we'd like to do. I mean, it's a single Gaussian, basically modeling a unit. I mean, we should actually have a mixture there, modeling a unit. And we've tried that. We haven't pursued it a whole lot. We haven't got it to work yet. You want a mixture model, a whole collection of...
You do a clustering, right, afterwards. So there is, in some sense, a mixture, because you might have 1,000 Gaussians in your SGMM, but you only have 64 clustered labels.
That's true, too. That's true, too. Yeah, but you're still ending up with one unimodal thing around that trajectory when you're when you're all said and done. You don't have any high spots and low spots in that space, acoustic space. So, yeah. Good. Rich.
So one question is, in the case where you're taking 15 minutes and you're labeling,
yes.
You're transcribing
yes.
those as words orthographically.
Yes.
And then you're trying to make a letter to segment SGMM model.
Unit. Yes.
If you skip that step and just treated the letters as phonemes,
yes, that's
that would be an alternative. So the question is, how much is the SGMM buying you?
I know that was on our list of things to do, using the letters as the units themselves, building a dictionary, and working that route. And it's a very valid approach. We just didn't pursue it. It may work as well or better. Or I don't know. I don't have the answer to that. Yeah. But again, it's only 15 minutes of training, and the question is how much training you need to build a mapping versus how much training do you need to build a recognizer. Right. Yeah, and
whether the SGMM is an intermediate level that's helping you with something. I mean, the advantage of the SGMM is you can train that on infinite amounts of data.
Yes.
For free.
Yes.
And then the question is, does that intermediate level help you or does it hurt you?
Yes.
Because it could do both. It could do either, depending on whether the mapping from letters to phonemes is a clean one.
Yeah, I know, and it's a very valid research point. I don't have an answer to that.
One thought, and I don't know whether it will help or hurt, is that in principle the 15 minutes could be from very few speakers, and your SGMM could still see a lot of speaker variability. But I don't necessarily know whether it will help or hurt, because when the units you see on the SGMM side of the bytext, if you will, all involves this particular speaker's SGMM labels. So I'm not sure whether it will help or hurt, but I can see that as one big difference.
Right. Well, the SGMM is trained unsupervised, so it may or may not model the same phonetic unit from different people as the same Gaussian.
Yes.
But it might, because it's got more context. It's got a whole segment. So maybe the shape is the same, even though the means aren't the same.
Could be. Now, I played some examples. First, we saw some of the, and in that Mubarak example, there were two very different things that sort of two very different speakers in this. Mubarak was in the same cluster. Yeah.
Same 5 gram.
Yeah, virtually the same 5 gram. It was slightly different. Yeah. Yeah. Okay. Oh, sorry. Just shout out, please. I didn't.
Two questions. One probably naive. I'll ask that one first. I'm interested in your trajectory-based approach. Would that be better than using standard HMM with GMM's first state?
With what?
Would it be better to model? Would it be better to model trajectories in ASR than what's typically done now?
Oh, well, the thing is, I gave that whole list of things that make the HMM very attractive. all the forms of normalization and context dependency and sets of rules and context clustering and all those things. We don't have.
But you could do all those things within an HMM-based model. It's just that the emission distribution would be over trajectories.
Yes, you
rather
could
than
do.
some exponentially decaying thing.
Yes, you could do it. It would take a lot of effort, I think, to do all that tuning. Yes, I think in principle you could, and maybe even end up with a better model, but there's a lot of work to be done. And so, to the extent you believe that the trajectory was doing could eventually beat the HMM, you might want to do that if you gave it all the sorts of additional information. But
Why
is
it hard to try, actually?
What?
Why is it hard to try? I mean, why can't you just swap it into a mature recognizer?
Oh, because one is based on the state idea and the state clustering, and there is special. Yeah.
I see why.
Yeah.
Some software engineering problem.
Yeah. Yes. Exactly. So VTL, yes, and I'm doing that. I'm doing some low-hanging fruit. Vocal tract length normalization you can do. That's not an issue. That's external to the HMM. Features that it's using, that's external, and all that stuff I will do, and I think we'll get improvements. Yes, but some of the internal stuff on how it deals with data, amounts of data, builds the trees, how to back off, all sorts of things you could do equivalently with the segmental models, but would take a lot of work. Just sheer work, I mean, just the hours. And we've all learned from one another in this community, and we've all relied on other people's work on what to do, and that's missing here. So.
I have a reaction to your question though. So you're thinking about an HMM in which the emission density in a state has a time varying.
It's variable length, yeah.
Has a time varying mean.
Correct, yeah.
Right? So that actually breaks the Markov assumption, right? Because then the output density depends on how long you've been in the state.
Yes, absolutely. That's right.
It'll break all the dynamics.
So I think, isn't it the case, I'm not a speech person, but isn't it the case that some people use explicit durations on the HMM so that the probability of a self-loop depends on how long you've been in the state?
Yeah, actually, Jason, there's also been papers where people explicitly put in trajectories, either defined parametrically or by a dynamical system, instead of an IID.
Oh, okay, so that has been done. So it doesn't, in fact, I'm just curious.
The experiments that I remember that were aimed at trying to do better recognition didn't. Esther Levin did that work years ago, and she tried them on digit recognition, and it didn't help. I'm not surprised, because why should it help digit recognition? That was already beat to death. But then Sandy and Gitsa, for some of their iPhone perception work, replaced the IID states by basically, trajectories and did DTW matching within it.
Sanjeev and Nash, wasn't there some form of modeling of this included in Karen Levesque's? Didn't the graphical modeling include the capability of representing trajectories in the augmented models?
Yes, she did. She had a variable which measured how long you were in the state, and that influenced the.
I remember watching to see whether that turned out to be, a big, powerful idea, but I think it got lost in the.
It wasn't a duration model. It was still, you were either in the state or it was a discrete.
Wasn't there a counter which?
Right. Even if there was a counter, that still wouldn't get you quadratically parameterized trajectories.
No, I thought it explicitly included trajectories.
So you can more complicated, not just a single hidden state.
Yeah.
I think there was some work on using linear models in states by, I think Wendy Holmes did some work along those lines, and Li Deng, Yeah. And it's somewhat different, unnormalized, but it was built into the states, but usually they stopped at linear.
Was there some work that maybe you and Manheim, or maybe Murray and Manheim, about polynomial trajectory models?
Oh, well, I think Manhung may have built a automatic segmentation, not having chop it up into segments. He extended the notion of, he solved that dynamic programming problem, of what happens when you add another frame and say you want to change your trajectory.
I did. I'm actually going to pull it off, though, because we're late at this point.
Okay, so let's see if anyone else has any last question. All right, otherwise let's thank our speakers once again.
Thank you.